In this session, we look at maximum likelihood estimates. So some of the random variables that we've been looking at have parameters. So the Poisson random variable has a parameter lambda, it's the rate. The normal random variables have two parameters, the expectation mu and the variance sigma squared. So sometimes the issue will be that for example, or you believe that there's a binomial random variable is the model for a particular experiment, but you don't know what the parameter p is. So you want a way of estimating that p. So given your idea of what the model is, which random variable is involved, and the results, and an unknown parameter in the model, then how should we estimate that parameter? So for example, we can flip an unfair coin. We don't know what p is in the distribution. So how would we estimate p? So let's say I toss a coin 10 times. I get h 3 times. What do we estimate is the probability of getting an h? Okay. So remember, the PMF for the number of h's, there are 10 flips. You have to choose x of them. The probability of getting x flips is given by saying you'd have to take the probability of getting an h x times 1 minus p to the 10 minus x. And then x varies from 0 to 10. Okay, and let's say your p is unknown. So I'm going to flip a coin 10 times. I'm going to count the number of h's. If I don't know what the probability p is of getting an h, but I'm going to take a look at my results, and let's say my results were 3 out of 10. So how would I estimate p? Okay. So then the probability that x is equal to 3, those are the 3 that I got, that would be 10 choose 3, p to 3, 1 minus p to the 7. Okay. So now consider this as a function of p. The probability of getting 3 flips is a function of this p. And we call that function the maximum likelihood function. We often write it as capital L of p semicolon 3. And now for different p's, we can plot that function, right? So we plot it for different p's with probability ranging from 0 to 1. And notice that there's a peak at now. This is a positive function, right? And all our probabilities are supposed to be positive, anyways, whatever we're doing. And so we can take its logarithm. So one thing that we could take the logarithm of that, and if we take the log, so we plot the logarithm of f of that maximum likelihood function, and we take a look and we try and find out where that maximum is. 0.3, I guess. So both the maximum likelihood function and the log of the likelihood function, the log likelihood function, they have a single maximum at the same value of p. So how can we find a value of p that maximizes let's write small l p of 3 for the log likelihood. So how can we find the value of p that maximizes the log likelihood of p3? We said we can take the derivative and we set it equal to 0, right? So if we say that 0 is equal to the derivative with respect to p of the log likelihood of the function L of p3, then that means that 0 is equal to the derivative with respect to p of the logarithm of this function. So now properties of log of the products is the sum of the log. So that's log of 10(3) plus log of p to the 3 plus log of 1 minus p to the 7. And then when you have exponentials with logs, you can pull the exponents downstairs. So that's d by dp log of 10 choose 3 plus 3 log p plus 7 log of 1 minus p. Okay, log of 10 choose 3 is a constant. So derivative with respect to p is 0. And derivative of 3 log p is 3 over p. And derivative of log of 1 minus p is minus 1 over 1 minus p. So you get that 0 is equal to 3 over p minus 7 over 1 minus p. And that gives us p is equal to 3/10, and that might be what we intuitively thought. Right? We would intuitively think this because of the law of large numbers. Right? Okay. So we estimate p. The probability p of getting ahead with the unfair coin is estimated to be at p is approximately 0.3. Okay, let's try another one. We have a multinomial distribution this time. So we have 10 independent trials. Each can result in outcomes that we label A, B, and C. The probability of getting A is P sub A. The probability of getting outcome B is P sub B, and the probability of getting outcome C is P sub C. Okay. And we might record our outcomes as, so there are 10 trials and there are 3 possible results. So we might use a 3-dimensional vector. So the first element in that vector would be how many trials resulted in A. The second element of that vector, how many trials resulted in B. And the third element of the vector would be the number of trials that resulted in C. So the record in N is N sub A, number of trials that resulted in A. N sub B, number of trials that resulted in B. N sub C is the number of trials that resulted in outcome C. So let's assume then that we can use the multinomial distribution. So that would be, there were 10 trials. So 10 factorial over N sub A factorial, N sub B factorial, N sub C factorial. The probability of getting an A to the power N sub A, the probability of getting a B to the power N sub B, probability of getting the outcome C to the power N sub C. Okay. The probabilities have to sum to 1. Probabilities are all bigger than or equal to 0. Okay. So now supposing that we got N sub A is equal to 7, N sub B is equal to 2, and N sub C is equal to 1. What are the 3 probabilities that we could, what are the estimates of 3 probabilities? Okay, so the maximum likelihood function, L of NP, we said was 10 factorial over NA factorial, NB factorial, and C factorial, PA to the NA, PB to the NB, PC to the NC. We got for NA, NB, and NC, we got 7, 2, and 1. And we got NA was 7, NB was 2, NC was 1. And so that would be N times PA to the 7 times PB to the 2 times PC to the 1 and P sub A, P sub B, and P sub C are unknown. Now, let's take the log of that. So the log likelihood function is log of 10 factorial over 7 factorial, 2 factorial, 1 factorial, plus 7 log P sub A plus 2 log P sub B plus 1 log P sub C, with PA, PB, and PC summing to 1. Now, what do we do? Well, we can use the method of Lagrange multipliers. So if we do that, then 7 over PA equals lambda, 2 over PB equals lambda, 1 over PC equals lambda, and PA plus PB plus PC is equal to 1. That would give us 7 over lambda equals P sub A, 2 over lambda equals P sub B, 1 over lambda equals P sub C, and 7 over lambda plus 2 over lambda plus 1 over lambda is equal to 1. And that last equation gives us that lambda is equal to 10. And then we get P sub A equals 7 tenths, P sub B equals 2 tenths, and P sub C equals 1 tenth. Okay, and again, these are what we might guess intuitively if we use the law of large numbers. Okay, x1, x2 up to xn are now identical independently distributed random variables, right? So they have the same parameter lambda. That's why they're identical. So probability that xi equals xi is 1 over xi factorial exponential negative lambda. Lambda to the xi. Okay, we don't know what lambda is. We want to estimate it. And then the probability of observing all of these results, these n results, is the product of the probability of observing the original results, right? Because they're independent. So we take the product of the probabilities, okay? And we can rewrite it this way. So exponential negative lambda n, lambda to the x1 plus x2, so on up to the xn, times 1 over the product I equals 1 to n of xi factorial. So this is the likelihood function. Now we take the log likelihood function. We'll get negative n lambda plus summation I equals 1 to n xi log lambda minus log of the product I equals 1 to n of xi factorial. Okay. Now what we want to do is we want to maximize the likelihood of seeing that exact sample. We're going to estimate lambda by some lambda hat. Okay. Now this is a function of lambda, so we take the derivative with respect to lambda, and we set it equal to 0. So if we take the derivative of this with respect to lambda, we're going to get negative lambda plus summation I equals 1 to n xi times 1 over lambda is equal to 0. I can take my n over to the other side. I can divide by the summation of the xi's, and then I can take the reciprocal. So I would get the estimate lambda hat equals 1 over n, summation I equals 1 to n of the xi's. Okay, so as an example, supposing that this is the, for n equals 10, this is what we got. This record of the results. Right, xi was x1 was equal to 0, x2 was equal to 1, x3 was equal to 0, and so on. Then my lambda hat would be given by 0.7. Okay, so these are 3 examples using the idea of the maximum likelihood. To find the likelihood function, it's going to be a function of the parameters. Then take the logarithm of that. You want to maximize that, take the derivative with respect to the parameter that you're looking for, set it equal to 0. When you have constraints, then you might want to use the method of Lagrange multipliers. Okay, so in general, you have a random vector x with a PMF or a PDF given by f sub x. The various values that x can take are written x. The probability or the probability density may depend upon parameters that are represented by vector theta, and these are unknown, and they're assumed to be constant. So we use the notation f sub x of x theta to emphasize that we are thinking of the PMF or the PDF as a function of the parameters in the vector theta. So the maximum likelihood function is this f sub x, right? And we're thinking of it as a function of theta. We take the logarithm of that, that's the log likelihood function. And we look for the theta that maximizes the log likelihood of seeing that particular outcome that you had for x.